Yeah, our next talk speaker is Ivar Martin, topological frequency conversion.
First, I would like to thank the organizers very much for giving the opportunity to present this work here, particularly so since the key ideas associated with this totally were actually generated at KITP about 5 years ago from our discussions with Gil Rafael. My other collaborators on this work include Bert Halprin, Frederick Nathan, Mark Ledner, Nisha Chandran, and Phil Crowley. So the main idea of what I'm going to talk about is the sort of how synthetic dimensions naturally emerge in driven systems, and then what interesting things one can do with those synthetic dimensions. So let us start with the outline. So first I'm going to show you kind of like perhaps a somewhat unfamiliar view of the K theory and how one can naturally interpret driven systems driven by a single tone, as having a synthetic dimension, essentially so-called frequency lattice. And then how this generalizes to multiple drives, and how multiple drives and commensurate drives generates multiple synthetic dimensions. Now, having that as playgrounds, one can actually ask, okay, so what kind of things we can implement, what kind of systems we can implement? And it turns out that perhaps the simplest interesting possibility is to create a topological insulator purely in frequency domain. So to illustrate what this thing may look like, so this is this little cartoon over here. Okay, so we can have basically a single quantum nonlinear system, like a single spin, which is being driven in this case by two tones, by two frequencies. And so the frequency conversion corresponds to taking the energy from one of the drives and putting it without loss into the other drive. And the topology, which this phenomenon inherits from quantum Hall effect, is that the rate with which this energy transfer occurs is actually quantized. So that was the theoretical idea, and now I'm happy to report that there have been a couple of experimental realizations using implementations rather, using MV centers, and also the same model was implemented on the IBM Quantum Experience quantum computer. And finally, at the end of this talk, I'm going to mention a couple of proposed realizations. So one of them really comes from far field, and I was really surprised to learn about this, that essentially the same phenomenon can be used to tell apart enantiomers, which is basically the mirror copies of the same molecule. As it turns out, that these systems on the nonlinear drive can also implement the frequency conversion. And also something that we've been working on with Frederick Nathan and Gil Rafael recently is how Weil semi-metals can really beef up this phenomenon to something which potentially could be even practically useful. So to begin with, so let me show you quickly how time in driven systems naturally leads to emergence of synthetic dimensions. So the setting is very standard. So we have a Hamiltonian, which is time dependent. So it has a constant part, but then it also has, in this case, simple harmonic drive applied. And so here I'm not specifying what the Hamiltonian is specifically. The Hilbert space can be arbitrary. Now, so instead of going straight up to the Flick-A eigenfunctions, let us represent a general wave function, time-dependent wave function, in the following form, where we separate out the time periodic bits, which are oscillating with different harmonics of frequency, and the rest of the wave function. So you can think of this as basically the phase factor that corresponds to a state with n photons. So this representation essentially separates out to an extent the photon part of the wave function and the rest. So even though when we're talking just about classical drive, we don't necessarily have to speak about photons, but implicitly they're present already at this point. Now what we do is we can take this wave function into the Schrödinger equation and collect the like terms, namely the terms which oscillate with the same total frequency. And what we end up having is something which is perhaps painfully familiar to anybody who took solid-state classes. We end up with the tight-binding Hamiltonian. So those amplitude psi n's become the amplitude, the on-site amplitudes of the wave function, and the constant part of the Hamiltonian becomes like an on-site potential, but now the amplitude of the drive essentially provides the hopping between the neighboring sites. Now, in addition to that, there is another piece actually which is quite important, which comes from hitting the exponential with the time derivative. So we have this on-site potential which is linear. So essentially, we have something like an electric field applied to the system. And okay, so why is it useful? Because we do have quite a bit of intuition about these sorts of systems, about lattices from solid state. So in particular, this model is nothing but a start ladder problem. And so we can try to use this intuition to do something interesting in the time domain. So this picture naturally, very simply generalizes to multiple drives. So for instance, if we have two incommensurate drives, so this frequency is omega-1 and omega-2, then again, we can come up with a very similar ansatz, but now we have basically the phase factors corresponding to each of the drives, omega-1 and omega-2. Again, we substitute it into the Schrödinger equation, and we end up now with a two-dimensional lattice. And the two-dimensional lattice emerges precisely because the frequencies are incommensurate. So a unique combination of n's, n1 and 2, generates a unique wave function that we can basically utilize as a Fourier expansion coefficient to single out those individual equations, the individual type binding equations. And now what you notice is that it looks pretty much the same, except that now the electric field that I mentioned from the previous slide becomes an electric field on the lattice pointing in the non-crystallographic direction. But the basic idea is still the same. So what we see is that this formally just time-dependent problem with some Hilbert space can be understood as a lattice problem in the fictitious space, or maybe not so fictitious space, in the space of number of photons of color 2 and number of photons of color 1. And just like in the usual start ladder, the electric field direction is confined. We cannot go too far because we, for finite local spectrum of this Hamiltonian H-naughts, we're limited in the energy range. So we're going to get some Bloch oscillations. But in the transverse direction, actually, we can go pretty far. So it is a legitimate two-dimensional problem in the presence of electric field. And now we can ask, okay, so is there anything interesting that we can do? And of course, we can just take an inspiration from the lattice problems and from the real space lattice, and perhaps the sort of thing which is most on the surface is topological insulators. And perhaps the simplest example of topological insulators is the so-called Bernoulli Zhang model, which is a sort of variant of a model that has quantum Hall effects without Landau levels, similar to the Haldane model. So this is the mass structure of that model in real space. So K is the wave vector in direction 1, direction 2. So just a simple type binding on a square lattice with complex hoppings. But what's interesting is that depending on the parameters, in particular on the relation between this mass, the constant part, and those coefficients B1, B2, we can end up either in the topological regime or in the trivial regime. And there's sort of nice geometry associated with this. So if you parameterize Hamiltonian in terms of the free vector, it is the wrapping of this free vector around a unit sphere as one goes around the Berlin zone that tells us the Chern number, and the Chern number is effectively the whole conductance. Okay, so there is a simple model, and so now let's just try to transcribe it into time. So probably many of you already guessed what one needs to do. So the transformation is very simple. The only thing I need to do, I need to transform the momentum into the phase of the drives. So we have two components of the momenta, and we have two drive frequencies. So this sort of correspondence does the trick. So instead of having the problem in the real space, now we have a problem in the time domain. And now the physics of it is really different. So it becomes more like an ESR or NMR problem, in the sense that we have a single spin which is being acted upon by magnetic field, and so they're all three components of the magnetic field. And if you look at the frequency omega-1, it's in the xz plane, and the frequency omega-2 is in the yz plane. So it's a little bit a complicated setup from the NMR perspective, but not insane. And the coefficient m is just a constant. You can think of it as a constant magnetic field. But again, this is something which has direct analog in real space. So we expect that the electric field, which we have built into this problem by virtue of having finite frequency, but not very high finite frequency, that's important. So we're sort of close to adiabatic regime. We anticipate that it's going to drive current on this frequency lattice in the transverse direction. And this is going to be our the analog of the quantum Hall effects, but in the time domain. Now, the analysis of the problem is quite straightforward, and theoretically, it just follows the same procedure as you would do for the usual lattice problems. So one can write down the semi-classical equations of motion. So this is actually written in the K space and real space. So this is the Berry connection, Berry curvature, and for the wave packets we have this equation of motion which involves the group velocity and the anomalous velocity. So this is all the sort of the standard stuff. And to go again to transition to the time domain, the only thing we need to do is to replace wave vector or momentum by the time-dependent phase of the drive. And as a result, we automatically going to have this dk dt, which is actually equal to the vector of frequencies. Okay, so that's the story there. And if you now push it a bit further, now in the photon language, if we have those two tones applied, the average drift velocity along the direction I is going to be given by the frequency in the orthogonal direction J, and on average it's going to be sampling the Berry curvature, which is of course related to the Chern number. So next step is to make it even more closely related to the topic of the workshop. We can multiply the n by the frequency of that drive. We're going to get the energy. So n times frequency is the sort of energy of all the photons in the drive, and therefore the time derivative of that is like power exerted by the drive on the system. And what we're going to find is that this power actually is pretty universal. It's opposite in sign for the two drives. So the energy is really being taken from one drive and put into the other without loss, and proportional to both frequencies. So I should mention here that actually Anatoly Popolnikov had a sort of a precursor of this formula written down some time before us. I think he wasn't looking at the periodic systems; he was looking at feedback perturbation theory for K systems. Okay, so this is kind of like you can still take it as a plausibility argument, but you can actually go and do the calculation directly. You can calculate the work done by each of the drives, so you see indeed that varying this mass parameter or the constant magnetic field parameter, as long as we stay within the topological phase, the slope, which is the power, doesn't change. But as we exit the topological regime, that's when the pumping power between the drives collapses. And one can relate the deviations from the perfection to the how well the spin actually tracks instantaneous magnetic fields. Because we are essentially utilizing sort of this nearly adiabatic regime. So the frequency is low and the drive strength is large. Now, it turns out that there's actually a lot of interesting subtleties, but phenomena that are happening here. And so one thing that we looked at was Phil Crowley and with Anusha Chandran is the possibility of actually zooming into this sort of fractional Chern number just at the transition between the topological and non-topological regimes. And it turns out that that's also possible to pick out this fractional Chern number of half by the protocol. And what's even more remarkable is that people were able to implement that experimentally. So this is the paper by Alex Sushkov and Eric Boris, where they collaborated with Anusha and Phil. And they in fact took single NV center and through very smart transformation to the rotating frame, they were able to implement this DHT model in the time domain, and they were able to access the topological regime, non-topological regime, transition regime, and they were able to track the evolution of the wave function, to do the tomography of the wave function of the spin, and indeed observe those interesting phenomena, in particular how the phase of the wave function on neighboring trajectories diverges if one is in the topological regime or doesn't do anything if one is in the trivial regime. So these are those plots underneath. So really, really neat paper. There was another experiment subsequently done by Daniel Maltz and Adam Smith, where they took sort of a ready-made spin, which is a qubit of the IBM quantum experience. And so they implemented this the BHD model on that computer, and they in fact computed the pumping power directly, kind of like the way you would do it theoretically, but on this quantum computer. So using sort of quantum computer in a way as a simulator for this problem. And indeed, they saw perhaps not surprisingly perfect agreement with the, well, almost perfect agreement with the with theory. Which again one can track back to a change of the Chern numbers in the topological and the trivial regimes. So now in the remaining couple of minutes, I would like to show you two more things which are which I think are quite interesting, and perhaps the sort of the most surprising thing that, as I mentioned, that I came across in the past year. Is this idea by Kai Schwennicke and Joel Yuanzhu, who realized that one can take a chemical system, a molecules that have sort of mirror symmetric partners, and one can implement the same kind of energy pumping protocol, frequency pumping protocol in the system. And what you need to look at three levels. So these are fairly complex rotor vibrational levels, and apply three drives with the amplitudes which are that are modulated. And it turns out that there's this interesting chiral product called Charles-Shapiro product, which changes sign as you go between the two enantiomers, between those two mirror partners. Which is kind of like, which is the reason why this works. But now, sort of at the formal level, what they show is that by going into the rotating frame, you end up with the Hamiltonian, which is very, very similar to the BHZ model, where you have control over all those drive coefficients, all those electric fields. The only difference being that we are no longer in S equal to half spin case, but we are in the, since we have 3 levels, we are effectively in the S equal to 1 limit. But that really doesn't change the physics, and so their proposal is that one can look at the energy pumping into the certain sidebands, and depending on enantiomer, you either get the pumping in positive direction or negative direction. And presumably, that could be a sensitive way to measure the imbalance between the left and right enantiomers. So finally, I guess in the remaining 2 minutes, also I'd like to mention work which is in progress, but it's really nearing completion fast, with Frederick Nathan and Gil Rafael, where we sort of addressing 2 issues with the original proposal. Namely, yeah, as interesting as it may sound, certainly it did sound interesting to us. If you try a single spin, I mean, it's not a sort of particularly practical situation, because you have just single spin, you can only get that much out of it. And plus, it's hard to create strong magnetic fields which are also really fast. So it turns out that by going to wide spin metals, this problem is solved thanks to the strong spin-orbit interaction in the systems. So just the gist of the idea, so this is the Hamiltonian for the via spin metal near one of the vital points. So now we turn on the external drive. By pile substitution, the vector potential lands into the Hamiltonian itself. And then lo and behold, you immediately see that we end up essentially with what we want. We end up with a product of the spin components and the drive. But now the drive is the vector potential, which is just the integral of the electric field. And the sort of the vital velocity can be quite high. So it turns out that the numbers are not quite there if you want to, if you're serious and you're taking into account dissipation and so on, but not too far off either. So for relaxation rates which are not too crazy, one can get indeed pumping power between the terahertz frequency drives. And so if you compute sort of count the number of electrons that participate and how much each one of those electrons contributes, you get the following pumping rates, which for favorable parameters can be for terahertz frequencies and like megavolts per meter electric fields, which is not crazy. One can get pumping powers of like 10 to 12 watts per centimeter cubed. And I guess that's quite dark, but he's quite interested about this sort of stuff. But there is, like, on the physics side, there's really neat geometry associated with it, and also neat material science, because there are interesting relaxation phenomena that have to be taken into account, and various nonlinear phenomena, even beyond this frequency conversion effects that become accessible in the biospheric methods. So to conclude, so I guess what I hope to convey is that yeah, it's very natural to think about the driven systems as systems in these synthetic dimensions, and I just focused on one example of actually of many that exist by now of taking advantage of those synthetic dimensions and trying to do something interesting there in terms of either energy transport or spin transport and other phenomena. There are some existing experiments, and there are some other sort of proposed ideas for the future. But I really feel like we're just sort of scratching the surface of those synthetic spaces. So there's much more interesting stuff left to be done. Thank you.
Great, thank you very much. There's already questions. Let's start with Anatoly.
Hi, Ivar. Thanks for the talk. I have like a few questions. So my kind of general understanding of this quantization was sort of it's indeed like very similar to quantum Hall. So I might think about frequency difference like between two drives, omega-1 minus omega-2, is time derivative of relative phase, right? And then conjugate to another phase will be basically energy. So in this sense, I would say that generically, as long as I have a gap, so probably I need finite number of levels, 2 levels, 4 levels, I should get like energy pump, which will be proportional to the product of the driving frequency times frequency difference and times sort of the Chern number. I just wonder, but you are saying that in these simple systems, it's actually more general. So frequencies shouldn't be different and so on. I'm just curious how generic it is. So if you have like 2 couple qubits, do you still expect like these formulas will work, or you really need to go to like slow frequency limit? Because usually whole response is linear response. So you need like a small velocity, right? Small.
Sure. And certainly we are in the, sorry, maybe I didn't emphasize this enough, but we're certainly in the slow frequency regime. So both omega-1 and omega-2 have to be small compared to the drive amplitude. So we are kind of like tracking a single instantaneous band. We looked quite carefully with Anusha and Phil at the alternatives, like when you drive faster, but then you need to do those tricks, kind of like the ones that you invented, or at least used, with the anti-diabatic terms to keep you in the same band. So there are ways to get away from adiabaticity, but in the simplest incarnation, you want to have slow drives, and the difference of frequencies somehow doesn't quite enter there, at least in this case. So yeah, I mean, there are simple generalizations where you look not at spin half, but you look at arbitrary spin, and then you just replace, you get the coefficient, which is the magnitude of the spin. So if you look at even more general situations, so let's say like a spin chain that's interacting, that's driven. So then, yeah, it's a different story. So I don't claim anything about that, and there's some work done in that direction with different questions being asked, but as far as pumping is concerned, I'm not quite sure if those systems would work.
Even like 2 coupled spins, like people didn't consider much. Spin chain might be just fitting.
Yeah, I mean, 2 coupled spins. Okay, so in cases where it reduces to like one, let's say 2 spin halves strongly interacting, converting into spin 1, I mean that would become a trivial case, which reduces to the one that we looked at. But more generally, I would, at least I'm not aware if people looked at that. So let's say a generic interacting 2-spin problem, and so seeing if there is a transfer. So I'm guessing there should be something if you drive strongly enough, but I don't quite know. So it reminds me a little bit of the stories with those multi-terminal Josephson junctions, where you can sort of see the random transfer matrix, and you can still get, once in a while, you can get interesting topological effects. You can get Majoranas and so on. So in a similar fashion, maybe with sort of a more generic system, you can also get sometimes something. But at least I'm not aware of kind of like a general trick or a general idea that would immediately tell me if there is energy pumping or not.
Okay, thank you.
Taran Grover has a question.
Hi, Ivar. This is Taran. I have a question about your BHZ model, or maybe question it in more general. But when we consider just standard real space hopping, and which gives you any topological phases, then there's a stability in the sense of any local perturbation. As long as Hamilton is local, it's a stable phase of matter. Now, when I consider your basically the single side problem, which has 2 frequencies, then where is the stability in the sense of, suppose I add some arbitrary, you have a very specific model which has 2 frequencies, but suppose I add some arbitrary time dependence, which is kind of, I don't see why I can't add some perturbation of that kind. Is it still protected, the topologicalness or anything like that? So because that would lead to a non-local hopping in this lattice, arbitrary
Right. So I think, yeah, so it's not, I mean, the model is not really fine-tuned in the sense that, so as long as you are sort of in the, remain in the same topological sector, the only condition is that you are nearly adiabatic, and then you can get this quantization. If you drive, let's say, if you add additional frequencies, or if you add noise, I mean, that's a slightly separate story. In fact, in the first paper was Gil and was Bert, we added some noise, and it turns out actually, if the noise is not too strong, it doesn't really destroy things. It can, in fact, stabilize in a certain way, not as well as, say, in the case of, you know, static disorder and quantum Hall effect, but it's certainly not a killer. But going back even to these standards, you know, like real space quantum Hall, yeah, I mean, you cannot apply a very large electric field, right? Otherwise, you just start generating.
No. So stability is not about the threshold, but as long as the threshold is zero or non-zero, that's what I'm trying to understand. As long as, and to me, suppose here I add an arbitrary time-dependent perturbation with infinitesimal coefficient, let's say. Is it a stable phase of matter for infinitesimal perturbation, but which is arbitrary time-dependent?
Well,
can we show that? I mean, is that
okay? So in the long term, even without perturbation, due to Landau-Zener transitions, eventually.
I see. Yeah, it will. Yes, true.
So in fact, if anything, adding Bath is a good thing, because it's and that's something we did with Frederick and with Gil. It sort of keeps you in the instantaneous ground state and keeps you pumping longer.
Mm-hmm.
So in this sense, it's pretty robust. And in fact, I mean, so I did mention a few other things that we've been thinking about, but I mean, the phenomenon has like a fully classical analog. You know, you can implement it with gyroscopes. So it cannot be that unstable. But, you know, if I asked you to create this kind of quantized response with gyroscopes without knowing quantum mechanics, you would be hard pressed. But with this quantum effects as already known, and it's actually quite straightforward exercise to show that classical systems should also exhibit this kind of behavior. So a lot of it is really semi-classical.
Okay.
Thank you.
Great. Thank you very much. And let's thank Ivar again.
Thank you.